Some of you may be here uh, for the second session and not the first. I'll remind you that this is operating under the note well. Please make sure you are following it. And if you don't know the things on here, please familiarize yourself so that you know what your responsibilities are. Please treat everyone with respect. And I'll remind you that we're managing the queue with the online tool. So um, use it to get in the mic line if you want to say something. And remote people, please mute and keep your video off while we're going, unless you're speaking. So, long day. Shriram, you're going to be up first with ASRA profile.
Give you only one set of slides for both of them together.
I just have to find it. There it is. Yes.
Hi. So this talk is about a new RPKI object that we call ASRA, Autonomous System Relationship Authorization. The motivation or the problem statement for this is that the ASPA-based verification, we have worked on it and perfected it in many ways, and it changes the status quo significantly with respect to AS path verification or route leak detection. So I think as a group we are happy about that and look forward to the deployment of it. So ASPA essentially can detect route leaks. That is what its strength is. And in addition to that, it can also detect forged origin and forged path segment hijacks. In a moment, I will explain what they are. I think many of you know it. And it can detect those when the update is received from a customer or lateral peer. So these are essentially fake link or forged peering attacks. Again, I'll show you a picture where that would become clear. The goal of this work is to detect and mitigate fake link attacks received from any direction, not from a customer, not merely from a customer or lateral peer as ASPA already is capable of, but in any direction means that the update can be received from a provider or a customer or a lateral peer. And in doing this, our goal is also to preserve ASPA's route leak detection capability. It must remain intact. So the verification, the way ASPA verification works, for the valid outcome, it requires an inverted V or an inverted V with a lateral peer at the top. So in this picture, 1 to 2 to 3 is an up ramp. Based on ASPAs, we determine that they are like customer to provider up ramp. Likewise, on the right side, 7 to 4 is also a ramp based on ASPAs, a provider to provider ramp. So if we look at, so the BGP update is moving from 1 to 7. That's the direction of the path. So 4 to 7 is, we call it the down ramp, and 1 to 3 the up ramp. Between 3 and 4, we may not have that lateral peer at the top. It may be a perfect vertical V in which case it's valid. And according to ASPA, it's also valid if it is anything else between 3 and 4. So 3 and 4 can be customer to provider, it can be provider to customer or lateral peers. Any of those relationships would be fine. In all of those cases, the ASPA verification algorithm determines it to be valid. So one thing that ASPA doesn't do is to verify whether 3 to 4 link actually exists, whether that peering relationship is faked or forged, or not. So that is where one can exploit this. So in this picture, 1, 2, 3 is an up ramp, which is validated by ASPAs, 1 to 2 to 3. X can be somewhere else in the internet, unrelated to this part of the internet where 1, 2, 3 are not connected. But X can fake a link to 1, in which case it would be conducting a forged origin attack, or it can fake a link to 3, in which case it would be conducting what we call a forged path segment attack. So 1 to 2 to 3 is valid anyway based on ASPA, and X can pretend that it is connected to 3, which it is not. But in the ASPA verification algorithm, this would be fine. The outcome would be valid. That is because at the top, that one hop, it can be anything. It can be a provider, a customer, or lateral peer. And in reality, if that were a real path, it is certainly valid without any leak. And so that's one gap in ASPA is what we are trying to focus on here to see if we can fill that gap. So this kind of shortcoming in ASPA can be exploited by an offender. In this picture, 6 is an offender, and 7 is the customer who is under attack. So everybody is doing ASPA, it could be doing ASPA, and 6 can still shorten the path to 7. So instead of the longer path, it can pretend a link to 2, and it can shorten the path. And the motivation may be for 6 to draw away the customer's traffic away from 8 and sort of increase its revenue, possibly. And these attacks could also happen sometimes due to accident. Another type of attack where it is not a provider attacking a customer, but a customer could also attack a provider if the provider is not doing ASPA. So this is a partial deployment scenario in which 6 can shorten the path to 7. 7 is not doing ASPA, and when 5 receives it, it computes to a valid outcome. So these are the type of problems that we are trying to address. The solution that's being considered here is to propose a new RPKI object, Autonomous System Relationship Authorization. It allows registration of customers and lateral peers. Either ASPA or ASRA must confirm a BGP peering link with the next AS at each hop in the AS path in the forward direction. So either one of these, ASRA or ASPA, can confirm that, yeah, the next hop in the AS path is connected to me. For example, ASI to ASI plus 1, it would be considered a fake link if ASI's ASPA and ASRA both exist and neither attests to a relationship with ASI plus 1. So I haven't told you what ASRA exactly is, but we'll come to that. But we make the combined use of ASPA and ASRA to detect these fake links. The ASPA alone method already guarantees that the AS path is feasible. ASPA plus ASRA together, the method based on them together, additionally can guarantee that the fake link or forged attacks are detected. So the subcategories, we have a few subcategories of ASRA 1, 2, 3, and you will, this tries to explain why we have that. ASRA 1 is used by the subject AS to register all customers. ASRA 2 is used by the subject AS to register all lateral peers. And ASRA 3 is an alternative to registering ASRA 1 and ASRA 2. And if the subject AS registers an ASRA 3, it will include the combined list of all customers and lateral peers in it without any differentiation. So if an AS doesn't want to disclose customers explicitly, it can attest a combined list of customers and lateral peers. So that is the reason for generating these 3 categories of ASPA or subcategories. So in the ASN.1, we have a subcategory field. We, of course, have the signer AS ID and the relationships, which is the relationships AS set. In addition to that, we have a subcategory and one octet devoted to that. The recommendations for ASRA registration, a subject AS that has ASRA must have an ASPA. So they are only useful together to confirm a fake link. So that is why that requirement. Therefore, ASRA without ASPA for a subject AS must be ignored in AS path verification. And an ASRA compliant AS must either register AS3 alone or register both ASRA 1 and ASRA 2. But in case an AS registers both ASRA, all of them, ASRA 1, ASRA 2, ASRA 3, then we can decide what to do. We can pick one of the two, ASRA 1 plus ASRA 2, or we can pick ASRA 3, or we can pick whichever between them gives us, seems to give us more ASS or something like that. That can be sorted out, and we can come to a conclusion on that, a decision on that as the working group discussions continue. To signal that an AS, assigning AS doesn't have a neighbors in a subcategory, it would simply put an AS0 in the relationship AS set field. In the draft, we have like laid out the complete detailed requirements for registration of ASRA for mutual transit ASS, complex relationship ASS, and route server ASS also. It's a little bit tricky. Alexander raised a good question about the route servers that are transparent, and motivated by that, we have included requirements for AS registration for route servers also, including the transparent case. So I'm not going to go into the details of that, but let's next focus on the verification based on ASPA and ASRA.
That's the second set of slides. You've got a big queue of people who want to talk.
No, it's not really. Maybe I could finish and then we can go to the questions. Yeah.
All right.
The path verification, the algorithm principles are that we want to preserve how ASPA by itself detects invalid outcome. So that like any route leak, we still want to be able to detect it based on ASPA alone. Only when ASPA has determined that an AS path is valid or unknown, then we would apply the additional verification using ASRA. So these are ASRA and ASPA are together used to determine if the AS path has a fake link. For any hop in the AS path, ASRA in the direction opposite to the update flow is never invoked in path verification. By doing this, we are preserving the sanctity of ASPA, that is, do not meddle with ASPA's route leak detection capability. So we add the fake link detection capability, but we do not meddle with the capability of ASPA for detecting route leaks. So we are improving upon ASPA by adding the ability to detect forged origin and forged path hijacks, as we described before, in all directions, whether the update comes from a customer, a lateral peer, or provider. Okay. Now, the algorithm has two algorithms, A and B. A is strict and B is stricter. So in A, what we do is that we look at each hop, K, and for example, K to K plus 1. And what we are suspecting is that K plus 1 can be potentially an offender. It might have created a fake link to K and passed on the update to its customer, in which case it is not detectable by ASPA. So what this does is to looks at the ASPA and ASRA of K and K plus 1. First thing is ASPA of K exists and does not include ASK plus 1, and ASRA of ASK also exists and does not include ASK plus 1. So that is K telling us that K plus 1 is not related to me. I don't have a link. And then we can give some leeway to K plus 1. And if we say that, well, K plus 1 put in an effort to register an ASPA, and it is attesting that K in the opposite direction of the path, K is my provider. So in that case, we can take that into consideration to determine that possibly there is a link between k+1 and k. So with that, I mean, that's why we call it strict, but not too strict. And the next algorithm, what it says that I'm not going to look at the ASPA or ASRA of k+1. We don't look at the ASRA of k+1 in any case anyway. That preserves the route leak detection property of ASPA, doesn't meddle with it. So we never look at the ASRA of k+1. But here in the stricter algorithm, we only look at what k is telling us about k+1. If k is telling us that k+1 is not in my ASPA, it's not in its ASRA, which means that k+1 is not related to k or connected to k according to ASPA or ASRA. In that case, that's a fake link. So once we have determined the fake link, what we do is that the combined algorithm using ASPA and ASRA is perform the ASPA verification alone, ASPA alone verification first. The outcome would be valid, invalid, valid, or unknown. If it is invalid, it remains unchanged. By doing that, like we are always detecting route leak first based on ASPA alone. And then once it is either valid or unknown, then if there is a fake link anywhere in the path, then we would change the outcome from valid to invalid or unknown to invalid. And then the couple of more slides, and then we can go to questions. Benefits to early adopters is that incremental benefits are accrued by early adopters. If an AS deploys ASPA and ASRA, then it prevents an offending AS from faking it. And that's because when the receiving or verifying AS also deploys, if it also deploys ASPA and ASRA, it is able to detect the fake link if the first AS is involved in a fake link at all. And this is independent of whether the intermediate ASs have adopted ASPA or ASRA. So in that sense, it's equivalent, somewhat like the property of ROA. If the first AS and another AS, they are doing ASPA, ASRA, then the first AS cannot be abused in a fake link attack. We have carefully laid out the operational and security considerations in the draft, and these are important for functionality as well as security. I'm not going to go into the details of those here for in the interest of time. With that, I can take questions, comments.
Okay, we have 4 minutes for questions.
Ben Workenline. Thanks for that. I think that all of your analysis in the first part of that presentation is correct, and I agree with all of it. I don't really recognize there being an actual problem to solve in any of it, though. Fundamentally, the gap that we're trying to fill here is the problem of lying transit providers, and that's just not a thing that I've ever observed in the wild. We're almost always talking about entities with some sort of commercial or business relationship between the two of them, and they don't tend to lie to each other because the consequences are severe when they do. So in that sense, I think that this is a solution going in search of a problem. The other problem that I have with this is that nothing about either ASPA or ASRA guarantees that people are not lying in the actual update message. That's why we have BGPsec. I think that if there is a problem to be solved here that is related to people lying about the existence of links between ASs, that's the correct solution to that is BGPsec, and we should focus our efforts on getting that into a state that it's deployable on the internet.
Okay, I mean, we are listing the attack by a provider towards its customer. We also show that in partial deployment, there is the possibility of an attack by a customer to the provider. So it's important to consider partial deployment also, such as this. In this case, 6 is a customer attacking a provider who is not adapted ASPA. And in turn, 6 is attacking 5 and making 5's traffic go through 6 to 1. So for these reasons, it may be good, maybe something that we need to also
My point is that all of the out-of-band objects in the world that talk about intended policy tell you nothing about the truthfulness of the AS path that appears in a BGP update. In order to do that, you need BGPsec. That's why we have it. I've also never observed that scenario in the world. But to the extent that it might exist, I still think that this is the wrong problem, the wrong solution to that problem.
Well, we can discuss. Thank you.
Alexander Azimov, Yango. You skipped a very important question. Please, can you, to the audience, tell how you see the operations of an ISP that is connected to a transparent IX?
Yeah, so you asked me that question and I answered it in email. The answer is that if you have a transparent AS, then the two clients, so there would be a hop in the AS path between two clients of that AS without the AS of the transparent RS. And so what we are proposing, but this can be discussed and refined, but what we are proposing for now is the client can list all the peers, all the other clients that it peers with at that AS. And the RSAS makes available the list of clients, and each client chooses which other clients it peers with. So it's just listing those in the ASRA.
Does the draft define the universal API to retrieve these data from each IX in the world?
No,
yeah, and what the trust model, of course, for this API.
No, we're not talking about the AS having to retrieve the list of clients from each RS. All we are saying is that the RS client knows which other peers it is peering with, and it can list those.
He does not?
In case he does not, then we also discussed that. It's basically all the other clients are its peers. If it doesn't choose some, then
he does not know the full set of the all clients of the IX.
Yeah,
and more than
that,
some of them may not be present at the route server.
Yeah, so this is
you
the
are already
starting
exposing the field.
Nice. Sorry, thank you. So this is the starting point. Was we started with one way to answer that question, but it can be potentially refined. Thank you.
Warren Kumari, Google with no hats. So this might be the best idea ever, or it might be the worst, but there is no space in my brain to even begin thinking about this till ASPA's all done, right? It feels like we should get that all done, published, deployed before we even think about.
Of course, yeah. We are not saying that we are stopping ASPA progress in any way.
Time on it.
Yeah.
Antoine Vuren, Liberty Global. Can you explain to me why you don't want ASFA records to be published before ASPA?
Oh,
that's on one of the slides you said, you
yes.
can't publish ASFA records if you don't publish ASPA records, right?
Yeah. So in order to determine a fake link, they are useful only if used together. And so if there is ASRA, but not ASPA, so if there is ASRA, we must have an ASPA also.
I'm a tier 1 provider. I don't have an upstream provider. I don't publish ASPA records. Because I don't have an upstream.
There is an AS0 option. If you don't have upstreams.
Okay, then I understand it. Yeah. I thought you meant, you have to have it first.
Yeah.
Okay.
Okay, moving to the next presentation.
You need that clicker back. Thank you, Shriram.
Okay. Which one? This is CISP.
Yeah.
Seems right.
Okay.
Good evening, everyone. I'm Libby Liu from Zhongguan Lab. Today, I will present the updates of the CISP object. In total, we have updated 3 versions for this draft. Today, I will present the version 02. Okay, before before introducing the main updates, I will repeat the background for the CSP object. First, remote peering is needed for a subnet adopting AS for exchanging the subspecific information with a remote one in the partial deployment. Mainly there are two reasons. First, IIS, whose source prefix is spoofed and its neighbors may not be on the path of the spoofing traffic. Second, IIS can use the subnet adopting AS near the attacker to filter the spoofing traffic. For example, S1 may establish the connections with S4 and to let S4 to help filter the spoofing traffic for S1. So the connection models can scale for exchanging the subspecific information between AS as more AS deploy subnet by following their operation recommendations. Here we provide two operation recommendations. The first one is to limit the maximum number of the subnet peering connections for IIS. The second one is to leverage the connected peering subnet adopting AS as agents for help forwarding their information instead of direct connection. CSP object is needed for the automatic peering. For example, the subnet agents or S1 and S4 need to find other subnet adopting AS and determine the one to establish connections. Automatic peering can help to reduce the operation overhead and accelerate the connection establishment between the subnet adopting AS. And CSP proposed a public API registry that contains RAS, which both deploy the subnet and are willing to set up subnet peering relationships. So a newly adopting AS can use this registry as a reference and pick the appropriate AS to set up the subnet peering relationships. So this is a summary of the comments, all of them from Russ. The first one is ASN.1 in the document incomplete and cannot be compiled. So Russ provides an ASN.1 module that compiles. Russ also suggested us to revise the class name or address family, and also reminded us there are two OIDs are needed in the inner considerations. So we have revised the name of the content type for CSP object, and we also revised the ASN.1 module to update the class name address family, the names of corresponding elements, and the format of ASN's module. Also, we added an additional validation step for CSP object. We also have revised the inner considerations. For the detailed updates of CSP object content, we have updated the format of ASN.1 module to make it be compiled correctly. And we have revised the class name to IP family addresses. The element IP address families, family addresses contain a sequence which contains one instance of IP family and one instance of IP addresses. The field of IP addresses contains an octet string, which is either IPv4 or IPv6. And the field of IP addresses contains a sequence of IP address instances. Also in inner considerations, we have added the requirement for two IDs. For next, we are going to implement the CSP and the ending comments.
Not hearing any. Okay, thank you.
Thank you.
Chris says they're in order on the list, the slide. So if you remember the last one you clicked on, the slide, there you go.
Okay, so
You can take it off the stand if you want, and you can freewheel it.
okay. So hello everyone. I'm Shuhe Wang from Zhongguancun Laboratory. Today I'm going to talk about the problem that even if every ROA is issued correctly and timely, there can still be certain types of route hijacks that can circumvent the route range validation. We summarize the problem as route partial visibility. For today's talk, I'll first explain what route partial visibility is and what security issue it may bring. And then we'll dig into the root cause of its formation by first making a classification of its type and then analyze the cause of each type. And finally, I'll give a short plausible suggestion to address or at least relieve the issue. So first, what is the definition? A route that is not visible to all ASs is called a partially visible route. Just like the example on the slide, only the route from ASA can be called as a fully visible, and all the other routes are called partially visible because only the route from ASA is received by all three routers. And to investigate its prevalence, we analyzed routes from 27 route views VPs across all 5 RIRs plus 1 Cernet VPs in Beijing. And we found that for most VPs, there is indeed a large number of routes that is not visible at the VPs, and numbers as well as the ROV states also shows great contrast across different VPs. And they suggest that the route partial visibility is indeed a widely existing problem. And so a direct consequence is that even if a non-loose BROA is issued timely and correctly at the arranged AS, which means all of its subprefixes of the maximus length is advertised. If one of the subprefix has no route at some other AS, then the local VRP at that AS will become loose instead. And we have also analyzed the routes we collected and find that the loose VRP at each VP is as high as around 36%, but on the other hand, the loose BROA is only far less than 10%, and such a huge gap can show that the route partial visibility is indeed does indeed make the great impact. And if a VRP is loose, it will mainly face two vulnerabilities. The first one is superprefix hijack. Just like the example on the slide, if an attack route if an attacker announces a route which has the prefix that is the superprefix of the prefix C, and then the route will be validated as not found no matter what the arranged AS is, and it will be the only advertised route for prefix C, and it will hijack prefix C. Another vulnerability is false range hijack, which means the attacker will fake a route which has the true arranged AS, but has the fake AS path that contains the attacker's AS. Just like the example on the slide, the attacker's route is still validated as valid, but since it is the only advertised route for prefix C, it can also hijack prefix C. To conclude, we can see that both hijacks is unable to define with current standard ROV. So upon the statement of the problem, we next want to know what has truly caused the route partial visibility, and we analyze the features of the partially visible routes and find that they can be generally categorized into 4 types. The first type is unilaterally partially visible routes, which means there could exist some ASs receiving no route whose prefix overlaps with each route's prefix. And in this case, it might be a result from getting dropped in the midway. And such routes take up most of the partially visible routes. And for all other routes, which we term as bilaterally visible routes, they can be further divided into 3 types. The first type we term as SPDO, which means the same prefix but different arranged ASs. And it could be a result from insufficient ROA registration of mouse prefixes. And the second type is DPSO, which means different prefixes but the same arranged AS, which could be a result from the broad deaggregation. And the third type, DPDO, which means both the arranged ASs and the prefixes are different. In theory, it could be a result from route aggregation. So it is reasonably to assume that the partially visible routes, they get dropped or changed in the midway in certain transit ASs by different routing policies. And then the downstream observer AS will either not receive the routes or receive the routes with the prefixes that can change their local VRPs to become loose. And that's how the different types of partially visible routes are formed. So what are the types of the routing policies that can achieve such effect? The first type is route filtering, which could contribute to unilaterally visible routes or SPDO pairs of bilaterally visible routes if mouse prefixes exist. The second type is route deaggregation in transit AS, which means which will suppress the original route and generate one or few routes whose prefixes are the subprefixes of the original prefix, while the orange AS is unchanged. And it can contribute to DPSO pairs of bilaterally visible routes. The third type is route aggregation, which will suppress the original routes and generate an aggregated route whose prefix is the superprefix of all original prefix. If the AS doing aggregation is the same as the orange AS, it will generate a DPSO pair. Otherwise, it will generate a DPDO pair. The ROV state of the aggregated route could be valid, not found, or invalid, can be one of all possible states. So in fact, it is also the most complicated routing policies to handle with this issue. So if the aggregated prefix is issued with the ROA and the AS doing aggregation is just the same as the ROA's AS, it will be validated as valid and do no harm to ROV. But if the aggregated prefix is issued with no ROA, whose prefix range doesn't fully cover the the aggregated prefix, it will be validated as not found. And in this case, if the attacker can just initiate a route whose prefix is both the subprefix of the aggregated prefix and the superprefix of the original prefix, and then the attack route will still be validated as not found and gets and it can make a successful superprefix hijack. And the third case is that if the AS doing aggregation is not the same as the ROA's AS, or if the aggregated prefix doesn't issue with any ROA, but it is a subprefix of another ROA's prefix range, it will be validated as invalid. But since we know that actually most aggregation is benign, but with the validation as invalid, they will just filter the aggregation route and make a route black hole. Solving the whole issue could be another substantial work, so it is not today's main focus, but I'll give a short, to complete today's discussion, I'll give a short suggestion. It seems really impossible to just coordinate all the transit ASs that have routing policies that can that is hidden danger. So a more practical proposal is just to solve the issue at each AS locally and defend against the attacks if they actually happen. So for fault range hijack, there are already many recent studies to focus on defining the attack. And commonly, there are main ideas to combine with AS plus features such as using ASPA. And for super prefix hijack, the local AS can either modify local VRPs to filter suspicious routes at RPK level, or just add specific rules for certain prefixes to the border router at BGP level. Okay, so to conclude, we have stated the definition and potential harm of route partial visibility, and we analyze the types of partial visible routes and what may cause each type of them. And finally, we gave a short suggestion. Okay, and that's all. Thank you.
Questions? Not seeing any. Okay. Thank you.
Hello everyone, I'm Sheng Lin from Zhongguancun Library. Today, let's talk about the problem of route-origin registry. According to the CIDR, around 10,000 mouse events every day, and 10 possible hijacking can found every day. So there are so many mouse events, legal mouse events every day. For example, multi-hopping and cost. So this draft target is to set the problem in distinguish between legal mouse and prefix hijacking. As we all know, the current route origin registry contains the RPKI or IRR. Sure, the IRR and RPKI can support the most, but there are some limitation, such as unreliable data quality and limited coverage and ROV adoption lag. Further analysis, there are so many IR database. Update time data is so long, over 6 years. What's more, there are so many bogans in the RPK and IR. Sure, some may be for special purpose. Despite the prefix coverage has increased, but there are so many mouse events prefix cannot be found in the R or RPKI. Among the matches prefix, some can be only one or subset or arrays. The is hijacking, route leak, or others. Is this why operators avoid ROV? Combined IR and RPK can improve the most events coverage, but there are so many different validation results. The same work registered in this different IR database, but so the most events may be registered in multiple IR database. Different networks may choose subset of IRs as their origin as their source for route origin validation, which can result in different results for the same announcements. Current synchronization protocol and management protocol doesn't matter this problem. Perhaps the new job by job in the afternoon can solve it. The operations filter IR database by RPKI. To face the challenges, some requirement is presented, such as multi-party governance, leverage multiple source data and cross verification to improve data quality and coverage. Build a law list to develop from the prefix users, serving as a supplementary current registry for prefix owners. Build the integrate with inter-domain routing and anomaly detection and multi-party governance to build a block list to mitigate abnormal route hijacking. So, to distinguish legitimate modes from malicious attacks, a variable complete high coverage route origin registry system is required. That's all. Thank you.
Any questions?
Chairs, apologies. I lost the URL of the on-site tool, so I couldn't get myself in the queue.
Is it
Joe
not
Snyder's.
on the sign there on the?
Oh, here there we go. It's so small.
Kids these days.
So you say there is limited coverage of ROAS. Is this about all prefixes in the routing system or just multiple origin AS announcements?
Oh, thank you.
In your slides, you assert that there is limited coverage of by ROAS.
Right there. Yeah.
Yeah.
Okay, so when you talk about there's limited coverage of ROAS, it's only about multi-origin AS announcements. In the RPK, you can simply create multiple ROAS to authorize multiple origin ASNs. So I am not certain what the problem is with the current system, because you can just create more ROAS if you have more origins. So can you clarify why change is needed, in your opinion?
Oh, thank you. I will consider it later.
Okay, no problem. Thank you.
Thank you, Rob.
Okay, thank you.
Second to last.
That one?
Yeah, I think so. No.
No.
That was the second to the bottom.
No. Those are yours.
It should be this PSVRO one.
Yeah.
Oh. I got the glasses so I can read.
I don't see it here.
What does PSVRO stand for? So we
What
can
was
find
the name of the
words.
slides?
Yeah, slide. Yeah. Speak up.
Problems.
Ah,
I
there you
got
go.
it. Found it.
Thank you.
Thank you. That it?
Hello everyone, I'm Ying Su from ZGC Lab in Beijing, China. I'm going to introduce overdraft RPK repository problem statement and analysis. Let's start with necessary RPK repository background. In RPK, CAs or RPK authorities can issue RCs and ROAs to subordinate INR holders. Each CA will upload RPK objects it assigns to the publication point it operates or designates. These PPs collectively from the global RPK repository. Relying parties periodically traverse all PPs, download and validate all RPK objects, and then generate VRPs to help board router make routing decisions. Today, RPK is important for securing inter-domain routing, but we found that the current RPK repository design will lead to three problems. The first one is reliability issue. Although current RPK is globally distributed, each CA stores the RPK objects it issues in the unique PP it runs or designates. It means that any PP's failure will hinder RPs from obtaining complete RPK object views. The second is scalability issues. Today, RP local cache refresh involved traversing all PPs to fetch updated data. However, the number of PPs and RPs are expected to increase with the further deployment of RA and RV. It may prevent RPs from obtaining updated data in a timely manner. The second is security issue. RPK repository is not tamper resistant. Authorities can unilaterally undermine any RPK objects without consent from the subordinate INR holders. Specifically for reliability issues, although RDP is designed to leverage to allow RPK repository to leverage CDN infrastructure to provide the service, but we found that only 9 out of 63 PPs are hosted in CDNs. We also found that 14 PPs carry the ROAs of the AS where they are located. It will introduce unwanted interdependency between the accessibility of a PP and the reachability of the PP's AS. It is obvious that PP blackouts affect RV. Repository PPs require high availability and network stabilities. However, our measurement showed that due to network instability, the time for RPs to refresh the local cache ranges from 64 seconds to 650 seconds. Current RPK repository also provides some solutions to improve its reliability. For example, RPK repository support two access protocols, RDP and rsync. However, only 8 repositories, RDP server and rsync server, are hosted in different AS. Measurement showed that at least 20% of RPs will not fall back to rsync when RDP fails. RPK also allows RPs to use cache data if they fail to sync update data, but cache data is prone to become invalid in prolonged outages, especially for crucial data with short validity periods, such as manifests. Meanwhile, using cache data to validate BP updates will increase the RV inaccuracy.
Very good.
One more time.
For scalability issues, as shown in the figure, the number of PPs has grown more than 12 times, from 5 PPs run by IRs to more than 60 PPs. We randomly sent a questionnaire to 2,500 RA deployers. Out of 68 responses, 24 operators said that they would consider running their own PPs in the future. It can be seen that with the further deployment of RA and the rise of delegated RPKI, there will be more and more PPs. And with the further deployment of RV, there will be more RPs. It means that RPs will need to access more PPs and PPs will need to serve more RPs. The increase in the number of bidirectional connections will increase the cost of RP refreshes. Furthermore, since CAs can run PPs at a low cost, PPs with unwanted purpose gradually merge, such as measurement. These PPs, when traversed by RPs, will only increase the burden on RPs, but it is hard to prevent the emergence of these PPs because in current RPKI, any CA has a right to run its own PP. Additionally, a series of work has demonstrated the feasibility of using delegated RPKI to exploit vulnerabilities in RPKI protocols or in RP softwares in implementations to store RPs or crash them. Although some RP softwares have fixed some issues, but it is difficult to prevent the risk fundamentally. The last one is security issues. As mentioned by RFC 8211. In current RPKI, the RPKI certificate issuance and management are all controlled by the RPKI authorities. So it is hard to prevent the malicious behavior by RPKI authorities, such as unilaterally delete, revoke, or corrupt or modify subordinate IAM holders' RPKI objects. In our survey, 44% of the AS operators have expressed concerns about malicious RPKI authorities. 2 operators said that they had lost all their RAs due to administrative or human reasons. RPKI also provides some solutions about this question. For example, RPKI community has provided a series of RPKI historical data tracking tools, but these tools cannot form a complete and consistent RPKI view, and these tools can only be used for performing audits after the fact. For IAM holders, they can also change CAs after the certificate being compromised by the upper level RPKI authorities. But it is difficult for them to rent IP from another city quickly enough and migrate network service from one IP prefix to another. RFC 8181 also say that API authorities can separate say engine and operations of repository functions. However, the choice of which repository to use is still designated by the API authorities, and operations on API objects stored in the repository PP are also performed by the API authority. So based on the above analysis, we propose the new API repository desired properties. First of all, the new API repository should not modify the API hierarchical certificate issuance architecture and be compatible with the current API repository architecture and support incremental deployment. Second, the new API repository should achieve truly distributed data storage, enable a single API object to be backed up across multiple repository nodes. Thus, the integrity of the API data accessed by RPs will not be affected even if a single PP experience a single point of failure. Thirdly, the API repository should prevent unlimited growth of the number of PPs and ensure timely updates of API data to RPs. Finally, the API repository should actively defend against API authorities' malicious behavior and maintain a complete and consistent API object view and provide audit functions for API. To summarize, in this draft, we analyze the API reliability, scalability, and the security issues from the perspective of API repository. Based on our overall analysis, we propose the desired property for a future API repository. Thank you.
Question?
Yes, basically, I agree this problem here, but one point that I feel like the scalability is more related to timeliness. So maybe it better to alter this kind of requirements or problems to timeliness because not only the time consumption to poll all these public points, but also the mechanism behind this kind of pull mechanisms maybe consume more time. So, okay.
Thank you. Thank you for comments.
I'm Chris. A bunch of the documentation here appears to be people know how to operate redundant, reliable services. I don't know that a bunch of work respecifying stuff helps.
Can you repeat your question?
Sorry, one more time. A bunch of the work you did points out that people don't know how to operate redundant and reliable services.
Oh.
Okay. Like I put my RP or put my publication point inside my AS. I only have one transit. So I have a SPOF, right? Somebody can, if my transit goes down, no one can get to my publication point, then my prefixes are at risk. That's one of your points, right?
Yeah.
Yes. So I don't know how to operate a reliable and redundant service. We should fix that problem. We shouldn't necessarily specify more restrictions, I think.
Oh, okay.
Right? Sorry. I guess my overall point is I don't think we need more specification. I think we need better training and better operational practices.
Okay. Maybe you can discuss more about the questions.
Yeah.
Mailing list. Thank you.
Send email.
Alexander Azimov, Yango. So you have presented some results from polls. Can you please clarify in which regions these polls were made?
Which region?
Yeah. So you have some pie chart that says about what engineers or I don't know who was participating in these polls. So what they think they should do. So in which regions these participants were asked? Yeah. So it was, for example, in China, or in Asia, in Europe, or globally.
Globally, I randomly selected RA deployers. Yeah.
So employers? Employees of deployers.
RA deployers. Yeah.
Okay, thank you.
I randomly selected 2,500 RA deployer deployed AS administrators and send a questionnaire to them. Yeah, and then get 68 responses. Yeah.
68 responses. Okay, thank you.
Yeah.
Okay, I'm going to have to apologize to the other speakers. We are out of time. The day is over. And so I'm sorry, we are not going to be able to do the last two presentations. Thank you. Wow, I thought the timer was helping, but I guess it didn't.